Okay, so forget the dusty textbooks and those impossible equations for just a minute. What if I told you that physics isn't just some subject in school? It's actually one of the oldest, most epic stories ever told. I'm serious. It's this global, multi-thousand-year quest, all to answer one single profound question. It's a story that didn't start in a lab, but probably with the first human who looked up at the stars and just asked, why? Let's follow the clues. I mean, just look at the world around you. The incredible arc of a rainbow, the raw power of a lightning strike, the silent, beautiful swirl of a galaxy millions of light years away. Heck, even the physics of how a car crumples in a crash. All of it, from the absolutely massive to the unimaginably small, that's the domain of physics. It's our attempt to figure out the fundamental rules of the game, the rules that govern how our entire universe behaves. And the name itself, it kind of tells you everything you need to know. It comes from the ancient Greek for knowledge of nature. See, before it was about particle accelerators and quantum mechanics, physics was simply about understanding the natural world. It comes from that fundamental human spark of just looking around and asking, how does all of this work? So, our story begins, and you should really think of it like a great detective story. For thousands of years, humanity has been on the hunt for clues, piecing together the evidence and trying to uncover the underlying laws of reality itself. And here's the thing, this story didn't just start in one place, not even close. From the very beginning, brilliant minds all over the globe were finding the first crucial pieces of this enormous puzzle. In ancient Africa, for instance, Egyptian astronomers weren't just charting stars for their calendars or mythology. They were doing something profoundly scientific. They were developing the very ideas of measurement. How do you quantify distance, or weight, or time? Without these shared, standardized tools, this language of numbers, no science is even possible. They were literally laying the bedrock for everything that came later. Okay, now this is where things get really wild. Just look at that date. Around 400 BCE, a group of philosophers in China called the Mohists wrote this down. If there's no opposing force, the motion will never stop. Sound familiar? It should. It's the core idea of inertia, the principle that Isaac Newton would formalize as his first law of motion, almost 2,000 years later. The same exact clue discovered continents and centuries apart. Amazing. And the baton, well, it gets passed to India. Scientists there were theorizing that sound wasn't some instantaneous thing, but that it actually traveled through the air in waves, just like ripples in a pond. And, this is critical, they were building the very language of physics. They developed advanced math, like trigonometry, and they gave the world a concept that would be an absolute game changer, the number 0. I know it seems simple, but without a symbol for nothing, the complex equations that run our entire modern world would be literally impossible to write. All right, now we get to the Islamic Golden Age, and this is a huge leap forward. Scholars like Ibn al-Haytham started championing a new way of thinking. You observe, you experiment, and then you reason. It was the scientific method, and he used it to completely overturn what the ancient Greeks thought about vision, proving that light enters our eyes, not the other way around. His work was so groundbreaking, it shaped scientific thought in Europe for over 600 years. So now we head to Europe, and this is where all these different threads, the measurement from Egypt, the math from India, the scientific method from the Islamic world, starts getting woven together into something totally new, a grand, unified theory of the entire cosmos. And all of a sudden, the pace of discovery just explodes. First, Copernicus puts the sun at the center of the solar system. Then Kepler figures out the elegant elliptical paths the planets take. Then Galileo points a telescope at the sky and changes everything. And finally, in 1687, one man, Isaac Newton, comes along and ties it all together in a beautiful package, publishing his universal laws of motion and gravitation. He basically wrote the rule book for the universe. And for the next couple of centuries, it really felt like we'd finally cracked the code. I mean, Newton's laws worked perfectly. They could predict the path of a cannonball and the orbit of a planet with incredible accuracy. The universe seemed to be this perfect, predictable machine, like a giant clockwork. If you just knew where all the pieces were, you could predict the future. It seemed like the great detective story was finally over. But then, well, every good story needs a plot twist, right? As our tools got better and better, we started to peek into realms way beyond our normal experience. The world of the incredibly fast and the world of the unbelievably small. And what we found there? Well, the neat, tidy rules of that clockwork universe didn't just bend, they completely shattered. This diagram does a great job of showing the new map of reality. See, up in the top left, that's our world. Normal sizes, normal speeds, that's the comfy home of classical physics. But as you start to approach the speed of light, you enter the bizarre world of Einstein's relativity, where time literally slows down. And as you shrink down to the size of an atom, you enter the truly weird world of quantum mechanics, where things can be in multiple places at once. Our common sense just wasn't built for this.
So the big takeaway here is that we suddenly had two completely different sets of rules. The classical world we live in is predictable, but this new modern world is all about probabilities, and it's quantized. Now that's a fancy word, but the idea is actually pretty simple. Think of it like this. Energy isn't a smooth ramp you can stop anywhere on. It's more like a staircase. You can be on step 1 or step 2, but you can never ever be in between the steps. The universe at its very core turned out to be fuzzy and kind of pixelated.
I love this photo. It just perfectly captures this moment of revolution. Look at these faces. You've got Einstein, Marie Curie, Max Planck, Schrödinger. Basically the greatest scientific minds on the planet, all gathered in one room, arguing and trying to wrap their heads around what this new physics actually meant for reality. They had to build a whole new understanding of the universe from scratch. And let me tell you, they did not all agree. And that, believe it or not, brings us pretty much to today. The story is nowhere near finished. We aren't at the end of the book. We've just reached the latest and maybe the most exciting chapter yet. So this is our current best guess, our most complete map of reality so far. It's called the Standard Model of Particle Physics. It describes every fundamental particle we've ever found, and it is fantastically successful. Its final missing piece, the Higgs boson, was confirmed in 2012. It's a beautiful theory. But, and this is a big but, we know this map is incomplete. Why? Because this map has some huge blank spaces on it. The stuff the Standard Model describes, that's only about 5% of the known universe. The other 95% is a profound mystery. What is this invisible dark matter that's holding entire galaxies together? What is this mysterious dark energy that's making the universe expand faster and faster? And the biggest question of all, how do we finally unite our two greatest theories, gravity and quantum mechanics?
And so, that leaves us right here, standing on the very edge of what we know. The human story of physics goes on. Are we finally closing in on a theory of everything that will tie it all together? Or is every new discovery just peeling back another layer, revealing a universe that's infinitely stranger and more complex than we can ever truly imagine? The quest for knowledge of nature is still very much on.